Going to start the binomial expansion by recapping some of the things that we looked at in AS. So these are the formulas that you should have seen at AS. So we've got this one here, which is probably the one that most of you are using. Some of you might have adapted it to use this one here. This can only be used when we've got a 1 plus at the beginning, so it has to be in the form 1 plus x. Okay. This notation here, so n1, you might have used it like this, so using NCR instead of the n1 in bracket, and it just relates to this expression here with the factorials. So just pause the video, have a go at expanding that, which you should have seen at AS, and see if you can get the answer. So just to remind us how this works, I'm using this top formula here. So the 1, so we take the first term in the bracket, and I've got that to the power of 4, and then it goes cubed, squared, to the power of 1, and then 1 to the power of 0, and we know that anything to the power of 0 is 1. Taking the second term in the bracket, so I've got a plus x here, that's going the opposite direction, so I've got x to the power of 4 over here, cubed, squared, power of 1, and then we've got x to the power of 0 here. Just remember that these powers here, they do add up to the power on the bracket. So we've got 2 and 2 there, I've got a power of 1 and 3 there. So in all cases that is adding up to that value there. And then we've got this 4c1, which, just to remind you of the notation, you might have seen it like that. Then we would simplify that down just by using the bracket. Have a think about expanding 1 plus x to the power of minus 2. When we're looking at that here, that minus 2 there is the thing that's going to cause us a problem. So just have a think about, maybe try and do minus 2, 2 on your calculator and see what happens, and have a think about how we might do it in this expansion here. This takes us on to the A2 content, where we are expanding 1 plus x to the power of n for any value of n. At AS, n was a positive integer, but now we can have any rational value of n. So looking at the formulas that we have dealt with before, when we have a negative value of n, so when we're looking at this formula here, we cannot, because this n1 relates to having factorial, I cannot work out factorial of a negative number or a fractional number. Therefore this formula is void. It only works when n is a positive integer. So we have to focus on this one here. Okay, it is given to you in the formula booklet and it looks like this. I'll talk about this notation in a minute, and we'll keep referring back to that because that is really, really important. But let's just have a look at the question we've just done from AS, but using this formula. So when we've got 1 plus x to the power of 4, just to get used to what the formula is doing. So the first term is 1, n here is 4, so then I get plus 4x. My next term is 4, and then n minus 1, 4 minus 1 is 3. And what you need to get used to doing is just writing this out without simplifying, just because it will stop you making mistakes as you go, and then we get that as x squared. My next term is 4 times 3 times 2 over 3 factorial, and that's x cubed. So if we just focus on that for a minute, what we have is when we're doing x cubed, I end up with 3 numbers here, 3 values here being multiplied on the numerator, and then I've got a 3 factorial on the denominator. So it's all to do with that power on that x, it matches up. So the next terms, it becomes quite easy to use. You don't need to look up your formula if you understand the structure. So the next one is x to the power of 4. So I want 4 values here. I'm just subtracting 1 every time. 4 factorial, and then I get x to the power of 4. So if you consider what would happen if I looked at x to the power of 5, we know that when we're doing something to the power of 4, then I'm going to get a polynomial that goes as far as x to the power of 4 and then stops. If we considered the next term, so if I did look at x to the power of 5, I'd get 4, 3, 2, 1, 0. All over 5 factorial x to the power of 5, but to be honest it doesn't matter now because I have that 0 in that numerator, and again if I continued and did x to the power of 6 it would go 4, 3, 2, 1, 0, minus 1. As soon as I hit 0 on that numerator and counting backwards, it's going to cancel out that term because when I multiply by 0 I get 0, and that is how this formula here is working when I am using an integer, a positive integer value. When we consider using this formula with a negative or with a fractional power, what we end up with is this expansion going on forever. So the formula is going to keep going forever, because what happens is if we put minus 1 in here, so I get minus 1, and then here I get minus 1, minus 2, for the cubic term I'd get minus 1, minus 2, minus 3. I've already gone past 0 and I'm not coming back to it because I'm going to keep subtracting off, whereas with this expansion here I do get to 0 because I started with a positive integer, which is why I get a finite expansion. Similarly, if I've got a fractional term, so if this is a half, it would go a half, then here we've got a half minus a half, we get a half minus 3 over 2, etc. You get the idea. Because of that, we are only ever going to have the first few terms of an expansion that goes on forever, therefore it's just an approximation, it's not exact. And then I said when we were looking at the formula, this formula from the formula book, that I was going to come back to this notation. So it's only a valid approximation when the series is converging. That means that it's getting smaller and smaller, so I can only use values of x that satisfy this. This notation here, we have seen it in vectors and we used it in mechanics to mean the size of the vector, and it's doing exactly the same job here. We focus on it a little bit more during A2 Pure Maths, but for now you just need to understand that that notation means that. So it just means that x is greater than minus 1 and less than 1. Most students think they're okay with this topic and get the final answer wrong in the exam just because there are a lot of different places where you can go wrong, either arithmetically or algebraically, so please be careful. So what I'm going to advise you to do is always write it out without doing any calculation. Check for brackets, check for minus signs, etc., and then it helps you just check that you've got your answer right at the end. Let's have a look at this question. So we've got a value of minus 2 for n. We're doing this expansion here. I have to use this formula because n is not a positive integer. So the first term is 1. Nice and straightforward. N is equal to minus 2. Like I said, let's not expand it out. Let's just write this down and get the structure correct. So I get minus 2x and put in a bracket around that minus 2. My next term is going to be quadratic, so I want two numbers counting backwards, so I get minus 2, minus 3. I've got 2 factorial here, so I've got 2 numbers there, 2 factorial here, 2 there. It's all matching up. Next term, cubic, I want 3 numbers on the top, minus 2, minus 3, minus 4, 3 factorial on the denominator, and the question has asked me to go as far as x cubed, and therefore I can stop at this point, and now this is when I would pick my calculator up. And that's what it simplifies to. So just check that you will get that using your calculator. Make sure you're using those brackets. Make sure you know how to use factorial. One thing to notice, if I've got n as negative, here I've got a negative term and here I've got a positive term, and it's going to alternate. That's because I've got an even number of negatives being multiplied on the quadratic, and then it goes for an odd number on the cubic, etc. Looking for the validity, that is focusing on the formula in the formula book, which gives us that. So the values for x for which this is valid is the modulus of x is less than 1. So just focusing on the idea of validity, we've got the same expansion we've just looked at. So this is 1 plus x to the power of minus 2, and I've got this set up as far as the cubic term, which is what we've just looked at. 1 minus 2x plus 3x squared minus 4x cubed, and the validity is modulus of x is less than 1. So just looking at this graph. So the blue graph is the expansion that we've got, so that's this cubic here. The red graph is the actual graph of 1 plus x to the power of minus 2, so that's the whole thing. And then this white bit here is the modulus of x is less than 1, so it's between minus 1 and 1. And you can see that around here, so around 0, we've got a really, really good approximation. And then as we get away from that, the approximation is not so good in both directions. The reason we want to focus on this is there's just a few points that we need to make. So first of all, let's set this so the highest power of our expansion is 1. So I've just taken the 1 minus 2x, which is a linear function. Obviously it's a really bad approximation here and here, but if you look around this point, so if we get really close to 0, even when we have a power of 1, we are getting a really good approximation. So when that value is really, really small, we're getting a really good approximation. As I make that power go up for my expansion, so as I include more terms in the expansion, you can see that we've got more values within our validity of minus 1 to 1 that are actually good approximations, particularly going up. In this case, when we're going up here, we've still got really close to the original expansion, and down here we're quite a way away. So the first thing to note is, if you are given values between minus 1 and 1, the best approximation is going to be the one that's as closest to 0, because with the least number of terms we are still getting a good approximation here. Okay. As we increase, so as we take more terms, we can get a better approximation for more values between minus 1 and 1. We're still, even when x to the power of 10, we've still not got a good approximation here. So you can see that it's the graph of the expansion is heading towards infinity here, whereas the graph is actually heading towards 0 here. So we've got different values here. But I think the thing to notice is if we change that highest power, so let's go for something a little bit bigger. It might take it a minute just to catch up. There we are. You can see that we've now got, as I've included more terms, so I'm going up to x to the power of 100, I've now got values almost all the way between minus 1 and 1. So the point of that validity is, to use values away from 0, we're going to have to include a lot of terms, so we're going to have a high value of x. But also, once, whatever power of x we take on this, once we get to 1, it will always be a bad approximation, and it'd be the same if we look up there, and it's going to be a long way up there to kind of look at the graph. But once we get to minus 1, the blue curve will fall quite a long way away from the red curve, so it's a bad approximation on that side. So the point is, the validity is a guide. If you take in a low number of powers of x, then you need to be as close as possible to 0, the smaller the better. However, if you take in more of the expansion, then you can go more within the interval that you're working with. Whatever happens, once you get outside that interval, you haven't got a good approximation. So moving on to this next question, slightly different. We need to think about our AS indices from the first topic that we did back in September. So what power would I need on this bracket, because that's going to give me the value of n, and then also looking that this looks slightly different because I've got minus 2x. One way to think about this is, if you look at this here, what I would do is I would write that down and just look at the comparison between it. So it looks like that when it is written down. So that gives me n is equal to a half, and then instead of x I have minus 2x, and you are going to use a bracket around that all the way through this expansion. And then it's just a case of structuring it. Like I said, write it down first of all. So when we do this expansion, we have 1. I'm using a half for n, so it goes a half, and then I've put, instead of x, I've got minus 2x in brackets. Half minus a half, 2 factorial, minus 2x squared in brackets. Half minus 2 minus 3 over 2. So this is just subtracting 1 off each time. I've got 3 numbers there, 3 factorial cubic. Watch out for this minus 2. That minus 2 needs to be cubed. So we saw that happen at AS, and quite a few people forgot to cube or square the value, the coefficient of x. So please remember that. If you've got this written down, it will pick you up all the method marks, but also it gives you a chance just to check the format of it and also come back and check that you haven't forgotten things like this. So the next step would be to put that into your calculator and simplify it down so we get this expansion here. State the values of x for which this expansion is valid. So it is normally valid for x is less than 1 greater than -1. Instead of x, just like I've had to use in the expansion, I've replaced x with -2x throughout. So I'm going to do the same with this here. That minus sign, we can ignore it because this modulus sign is telling us that we're just looking for the size of 2x, and what I'm going to do, because I want the modulus of x is less than, I'm going to just divide through. So I end up with the modulus of x is less than 1/2. If we just consider that for a moment, going back to this notation here, just to convince yourself that this is okay, if I had this notation here, then I would divide through by -2. So when I divide through by -2, I end up with that. And remembering that we have to change the direction of the inequality when we divide by a negative, just because that, to make it make sense, we would end up with this, which I would write the other way around. So you would write it like that, which is exactly the same as this notation here. Focusing on to the next part of the question, so we need to use the expansion to find an approximation for the square root of 0.8. We already have our expansion, or the start of our expansion, remember it's an approximation, and we know that x needs to be between -1/2 and 1/2. What I want is for this here, so 1 minus 2x to equal 0.8, so that's my starting place. Okay, so I need 0.8, whatever it is that I'm looking for, to equal whatever the expression is inside the bracket, and it needs to fit in this interval here. So by solving this equation, you should be able to arrive at x is equal to 0.1. So maybe just pause the video and convince yourself that that's the case. So we can use it in the expansion because it does satisfy that. When you're asked to do this, we then need to substitute that value into both sides of this expansion. Now, we sometimes get asked this in terms of the exam question. They'll ask you to describe what you're doing or explain what you would do. When you explain what you're doing, you have to say, I would substitute x equals 0.1 into the square root of 1 minus 2x and into the expansion on the right hand side. Okay, so you need to highlight that you would do it to both sides. And then it's a case of calculating both of these. So when we get that, we end up with this here. So the square root of 0.8 is approximately equal to 0.8945. The true value of this is 0.89442. So you can see that we are correct here to the first 2 decimal places, the first 3 when we're not rounding. Which if we added more terms, the idea is if we add more terms into this, then that would change this, and we'd get more decimal places out of that. So let's have a look at this example again. So we're still working with the expansion we've just done, and here it is at the bottom, just to remind us, and this is our validity. But just think about what would happen if we substitute x equals -2 into the expansion to get an approximation for root 5. So substituting it into there gives us root 5 is equal to 5. That's just using this part of the expansion here. We would need extra bits on, obviously, if we continue to use the expansion, but you can see that root 5 is equal to 2.3263 decimal places. We are a long way away from that. It is a really poor approximation, and it's because we're outside that range of validity that we decided we needed to use. So let's just focus on why we have this validity range and where it has come from. So if we're raising a number that is greater than 1 to a positive power, it is going to grow. It's going to diverge out of control. What that means is the value of -2 to the power of 10, for example, is a lot bigger than -2 cubed, which is a lot bigger again than -2. So the powers that we need that have the greater powers on there are going to have more of an effect on the approximation than these powers near the beginning. But the problem we've got is this is an infinite expansion, and therefore to get this value here we need the full expansion, which we can't have because it goes on to infinity. So what we have to do is take a value of x that's between -1 and 1. Remember here we had 2x in the position of x, which gave us that range between -0.5 and 0.5. The reason being that when you substitute -0.5 or 0.5 into the 2x, that puts us back into this range here. When we raise something in this interval here to the power of 10, it's a lot smaller than if we're raising something to squared or something cubed. So therefore what's happening is these values are tending to 0. So the 2x to the power of 100, for example, would be so small that it's not having a major effect on the approximation. And if I'm only looking for a few decimal places, I only need to take the first few terms because they are having more of an effect than the values that are tending towards 0 further down the expansion. So the validity of the expansion is dependent upon the value of x we substitute into the terms, and we must remember modulus of x less than 1, that's what you're given in the formula book, is exactly the same as x is greater than -1, x is less than 1. That's exactly what it means, less than 1. And just to briefly look at that expansion on the graph, so here we've got the validity from -0.5 to 0.5. The red is the square root curve. Remember, because it's square root, we've only got the positive here. If I was to include the negative square root, it would curve underneath, so we'd have a reflection of the red curve down here, so we'd end up with a backwards C shape. And the blue is the expansion. I've got it set up to the cubic term, so that's the one that we were looking at in our expansion. And you can see that actually even the cubic is a really good approximation for nearly all the values between -0.5 and 0.5 on this one. Close to 0 again is exactly on top of the curve, so that's given us the value, but even when we're coming to this -0.5 here, we're getting very close to our original function. We have just substituted -2 in, so we were looking at substituting -2 in, and you can see it's not even showing up on this screen, so we'd need to look further up the graph. It's a long way away because I'm dealing with a cubic, and we know that cubics head off to infinity here, whereas this square root graph has obviously got a shallow gradient, so that's tending in that direction. So they're heading away from each other. I cannot use anything over here, but within this interval here for these small values, we are getting a really good approximation. So we're going to have a look at this exam question here. It's got two parts to it, and it looks a little bit complicated to start off with just because you've got a fraction. With the binomial expansion, the first thing that you always need to do is get it in index notation. The best thing to do is to put a bracket around your numerator and your denominator, and then get it all so that it forms on one line of the algebra, like we've got here. I'm not really interested in that 3 minus x because it's got a power of 1 on it. I know how that expands, but I need to do something with this. So step 1 is to expand that. So I want you to pause the video, please, and do an expansion of that. We're going up to x to the power of 4. There's the formula that you would need to use. So in this example, we've got n is equal to -2. When I substitute that into the formula, remember I'm going up to x to the power of 4. It looks like this. 2 numbers, 2 factorial, 3 numbers, 3 factorial, 4 numbers, 4 factorial, brackets around the minus signs. Okay, simplify that down, and this is our expansion. So to continue, what I'm going to do is I'm going to take this as a bracket and substitute it back into here so that I can expand it with the 3 and the minus x. So going back to that fraction, this is what we've got here. Now remembering that I only want to go up to x to the power of 4, so the 3 is going to multiply every single term in here, but the x can stop at the cubic when we expand it, because when I do x times x to the power 4, that takes me outside the terms that I'm looking for. The reason why I'm not going to include it is because if I wanted the x to the power 5 term in this expansion, I would need the x to the power 5 term here for the 3 to multiply by it. So that x times that 5x to the 4 is only going to be part of the expansion. So just expand that out and check that you can get to here, because this is a simplified down version. So I'm doing 3 times 1, 3 times minus 2x, 3 times 3x squared, etc. and then collecting like terms to get to this point here. Okay, I would show that intermediate step as well in my working out, and I would watch out for that minus sign. The value is valid for the modulus of x is less than 1, so that's that bottom bit there. That is coming from this expansion here. So when I've got more than one thing that I need to expand, I'm going to look at the validity of both expansions and take the smallest one. So 3 minus x would be valid for all numbers. The 1 plus x to the power of minus 2 is only valid for modulus of x is less than 1. Therefore, because that is a smaller range, that applies to the whole thing. Looking at this question here, so I want to expand 1 plus x over 8 to the power of a half in ascending powers of x up to and including the x squared term. So in this example we have n is equal to a half, and then instead of x I need to use x over 8. The 1 plus can stay, that matches, but the x needs to change to x over 8. Like I said before, let's write this out without doing any simplification. So have a go at expanding that and then simplify it down and see if you can write down the range of values for x for which this is valid. So pause the video and have a go at that. So your answer should look something like that in terms of its working out. Notice I have brackets around all of these terms here. That squared is going to affect that 8, so that is x squared over 64. I'm going to bring the 64 into this to find the coefficient of x squared. So we end up with 1 plus 1 over 16x minus 1 over 512x squared. The range of values for x, well, I'm using x over 8 instead of x here, so it will be the modulus of x over 8 is less than 1, and then I would take any coefficients that I have here and get them across to the other side of the inequality, so I've got modulus of x is less than 8. This last part here, so hence by writing x equals 1 in this expansion, show this. Okay, so when you substitute x equals 1, remember it has to be between minus 8 and 8, that's what that's saying, so this is okay, this is fine. I need to substitute it into the left hand side and the right hand side of the expansion, so I'm going to substitute it into both sides. So I get 1 plus 1 over 8 to the power of a half on the left hand side, and then I substitute 1 into there, which gives me this. I want root 2. Okay, so that's what the question has asked me to do. So what you're going to do with this is simplify it down using surds. So square root of 9 is 3, square root of 8 is 2 root 2. So if I divide this by 3 over 2 and then take the reciprocal, i.e. flip it, I should end up with root 2. Okay, so we are flipping these both over, so I've got 5, 1, 2, which is the denominator becomes the numerator, 5, 4, 3 goes onto the denominator, and then flipping that over. So what we're doing here is we've got 2 root 2 over 3 and 5, 1, 2 over 5, 4, 3, multiplying 3 by 3, dividing 3 by 2. I think when we get a question that looks like this, because we're substituting x equals 1 into here and we don't just get root 2 straight away, a lot of students just leave this one. What you want to do always when you're doing this type of questions, you're going to substitute that value into both sides and then see what you've got, and even if you can't spot it, you will get some marks for doing this step here, but generally put that into your calculator, see what it gives you, it will simplify it down for you, and then you should be able to work out what you're doing to get that approximation.